So the chapter 6 review's got to be long. It's a long chapter. The test is worth 150 points. So I'm just going to jump into it, but it's probably going to be a two-parter. The first question has two parts. The first part asks me to find f composed with g of x. And we should remember that f composed with g of x is the same as f of g of x. And that's nice because that just tells me to take each of these two x's and replace them with a g of x. So I'm going to start with that. F composed with g of x is going to be, I'm going to take that x and change it to g of x because it means f of g of x. That's what I'm going to change the x to, is to g of x. And then plus 2, and I'm going to take that x and change it to g of x. And then plus 3. So there's my f composed with g of x written with horrible function notation. All I'm going to need to do is clean up that function notation. I'm going to replace the function notation with what it's equal to. So I'm going to take in each of my parentheses, I'm going to take the g of x and change it to 4x minus 1. So I'm going to change this to 4x minus 1 squared plus 2 times 4x minus 1 plus 3. And then I'm going to clear the parentheses. The first parentheses is the sneaky one. If I don't do it properly, I'll get some points off. So I'm going to, before I square 4x minus 1, I'm going to write it with two parentheses to do the foiling, because 4x minus 1 squared is really a foiling problem. And if you don't rewrite it as two parentheses, you'll probably miss the foiling part. So I need to do firsts, which are going to be 4x times 4x, which is a 16x squared. Outers, which are 4x times minus 1, which is going to be a minus 4x. Inners are a minus 1 times 4x, which is going to be another minus 4x. And lasts, which are minus 1 times minus 1, which is going to be a plus 1. Got the first parentheses simplified. Haven't combined the outers and the inners yet, but I'll do that in a second. Now I'm going to clear the second parentheses by multiplying 2 times 4x and getting a positive 8x. And 2 times minus 1, which gives me a negative 2. I'm going to bring down the plus 3. Now I'm going to combine my like terms. The 16x squared that's written first doesn't have anything to combine with it, so I'm going to leave it written first and not worry about it anymore. The minus 4x and plus 8x need to be combined, and I think that actually cancels because the numbers in front of there, minus 4 plus 8, give me a 0. So in the next line I could write a 0x, but those terms are going to cancel because this is a minus 8x, that's a plus 8x, and those will cancel just fine. They don't need to be in my answer. The number part, the plus 1, minus 2, and plus 3, I can go 1 minus 2 plus 3, and I'm going to get a plus 2 on my calculator. So after the 16x squared, I don't need an x to the first power term because they cancel, but I need a plus 2 for the numbers. This would be considered an okay answer, but probably because there's a common factor, I should pull that common factor out as I go to write my answer. So the best answer, I think, for problem 1a would be f composed with g of x equals to 2 times 8x squared plus 1. Back in section 6.1 where we actually did this for the first time, if you remember this, to find the domain of this kind of problem, because f of x is a polynomial, it's a parabola, g of x is a polynomial, it's a line. Both parabolas and lines, both f of x and g of x, don't have any restrictions to their domains. Both functions f of x and g of x have domains of negative to positive infinity. That's going to be the case for the domain of f composed with g of x. There's going to be no algebra to do this domain. And we're just going to say the domain is the interval from negative to positive infinity. We could write the words the domain is all real numbers, but it's a lot easier just to write this interval. So we'll just stick it right there and be done with this part. The next part's a little bit trickier because it's the fraction version. The find each function's harder, and the domain is trickier as well. So to do 2a, again, I have to remember that f composed with g of x means to find f of g of x, which means to change that x to g of x. So I'm going to just do that for my first step. F composed with g of x is going to equal 3 divided by g of x. And now I'm going to replace the g of x and get this horrible mess. So I'm going to get f composed with g of x equals 3 divided by 1 over x minus 4. Didn't really leave myself enough room to do that algebra, so I'm going to do this algebra off to the side. So this 3 divided by 1 over x minus 4, I can rewrite this instead of having a 3-layered fraction. I can write it as 3, change that fraction bar to a divide, and leave the 1 over x minus 4. The nice thing about getting it from a 3-layered fraction to a division with fractions is it's more clear what to do. I have a division problem to the right of the division sign as a fraction. I can change that division problem to a multiplication by taking the reciprocal of the fraction that's to the right of the division sign. Now that I have the problem written with a multiplication symbol, I'm going to be able to get rid of the fraction because that fraction has a 1 in the denominator. And I'm going to get rid of the multiplication symbol because I can make something that implies the multiplication. I'm going to change this to 3 times x minus 4. Should probably write equal signs. This line is equal to the one above it, which is equal to that, which is equal to that. And now I'm going to clear the parentheses. Said this, I need to go 3 times x and 3 times minus 4. This means 3 times the quantity x minus 4. Might have even been nice if I had a parentheses there. The parentheses there really weren't necessary because I had the fraction that implied the numerator is in a parentheses. But I'm going to clear these parentheses and go 3 times x and 3 times minus 4 and get 3x minus 12. It's actually a really nice, that's my answer, other than I haven't pulled out a common factor. So that algebra came out a little bit cleaner than some of the algebra that we did when we did section 6.1. This would be an okay answer, but the answer that I'd like you to write is that with the common factor of 3 pulled out. So a best answer for problem 2b would be f composed with g of x equals 3 times x minus 4. To do the domain of this, we have to do it in 2 steps. We have to do the domain of the g of x first, and then integrate that with the domain of our answer. So there's 2 steps in finding the domain. So first we're going to find, or start finding the domain of g of x. We're finding any number that needs to be excluded from the domain. When I say we're finding the domain, it's not full out the domain, but the algebraic part, finding the number that needs to be, finding any number that needs to be excluded from the domain. So when we do a composition of functions and there's fractions, first we'd find the domain of the function that's written to the right of the composition, and then second we're going to find the domain of the answer. And back in section 6.1, this usually involved 2 bits of algebra. And each part of the algebra gave us one number to exclude from the domain. So the first bit of this, I'm finding the domain of the g of x. The g of x is a fraction. To find the domain or the number to be excluded from the domain in a fraction, you ignore the numerator, you set the denominator equal to 0, and I need, for this particular answer in part B of number 2, I need to exclude 4 from the domain of my answer to part B. Because if you plug 4 in for g of x, you get 1 over 0, which is undefined. I move down to my answer now. If my answer was a fraction, I would do the same algebra, meaning set the denominator of the fraction equal to 0 to find the number that needs to be excluded from the domain. But because this answer is a polynomial, there's no number to exclude from the domain from it. That by itself, it has a domain of negative to positive infinity. It's not a fraction. It doesn't have a logarithm. So that I don't pick up an extra number to exclude from the domain because, again, because it's a polynomial, and polynomials have domains of all real numbers. So what we did back in section 6.1 is we integrated these two parts together. Usually there was a number to exclude from the first computation and a number to exclude from the second computation. And as we wrote our answer, we would just say the domain of f composed with g of x. I don't have that much room, so I'm just going to say the domain is all real numbers except, and then it's definitely except x equal to 4, and then generally we'd have another number to put after that from the computation from the second part of my work. But because the second part of my work involved finding the domain of not a fraction but a polynomial, there isn't an extra number to include. So here the domain would be all real numbers except 4. Usually on the test from section 6.1, I ask a question like problem 1 and don't ask a question like problem 2 for what that's worth. Alright, so moving on to something that's a little easier. So questions 3 and 4 give me two functions, and we're asked to find which of the functions are 1-to-1, and if the function's 1-to-1, find its inverse. So there's two parts for each of these questions. I probably could have written it as a question A or question B. First thing I need to do is determine if the function's 1-to-1. A function is 1-to-1 essentially if all the y's are different. If I look at question 3 and I just stare at the y's, all the y's are different. So I can say f is a 1-to-1 function. And then if a function is 1-to-1, find its inverse. So because in problem 3, f is a 1-to-1 function, I'm asked to find its inverse, and that's real easy to do. So right under the statement that f is a 1-to-1 function, I'm going to write its inverse. To write the inverse of f, I'm going to write the f function with the inverse symbol. So this tells me I'm finding the inverse of f. And I'm going to create the inverse. And inverses, when functions are written as points, are very easy to find. You just flip each point's x and y. So that's all I'm doing. The point 0, 1, I flip to the point 1, 0. The point 1, 4, I flip to the point 4, 1. The point 2, 0, I flip to the point 0, 2. And the point 3, 5, I'm about to flip to the point 5, 3. And that's everything that's asked for me for problem 3. I determined that it was a 1-to-1 function because all the y's are different. Because it was a 1-to-1 function, I found its inverse. For function g, if I look at it, it has 2 points that have the same y. So g is not a 1-to-1 function. So that's determined whether the function is 1-to-1. That's what I've done. I don't need to find the inverse of g because it says if a function's 1-to-1, find its inverse. If it's not 1-to-1, I shouldn't find its inverse because its inverse isn't a function. So for question 4, there isn't anything more to do. I just stop right there. I said it's not 1-to-1. Because it's not 1-to-1, I don't do the extra part to find its inverse. Question 5 gives me a graph of a 1-to-1 function. That function's called f, and I'm supposed to graph its inverse. Super easy to graph inverses. The 3 points that are marked in the function are the point -3, the point 1,2, and the point 6,3. Since those are in the graph of f, and I'm asked to graph f inverse has to have on it the point 0, -3, the point 2,1, and the point 3,6. On top of that, the inverse needs to have the same shape, which is kind of a half a parabola. So I'm going to graph these 3 points, 0, -3, 2,1, and 3,6, and I'm going to connect them with a half a parabola. Because this is the starting point, its flip is going to be the starting point. And I'm going to graph my half parabola, and that's all there is to do. That's the graph of the inverse. You don't have to take the time to graph the y = x line that goes through the origin to show you that the inverse is, properly graphed. All you have to do for this is just take the points that are given in the original function, create the points of the inverse, which are just flipping the x's and y's, and then after you do that, you just connect those points with the same shape, in this case a half a parabola. Six asks me to find an inverse in part A, and to find an inverse we went through a few steps. So for 6a, the steps to find the inverses is first, we're going to change the function symbol, the f of x, to the letter y. That's going to give me y equals x cubed minus 5. And the reason we do that is because it makes it easier to do the algebra. Now we're going to actually create the inverse by switching the x's and y's. This will give me x equals y cubed minus 5. And then we do the algebra. We're going to solve for y, and that's going to take 2 steps. I'm going to add 5 to both sides. And that's going to give me x plus 5 equals y cubed. And then I'm going to cube root both sides. I'm going to cube root the left side, and I'm going to cube root the right side. On the left side, that won't simplify. I'm just going to get the cube root of x plus 5. And on the right side, cube rooting cancels out the cube and leaves me with the y. I'm technically done. Now I'm going to replace the y with an inverse symbol and write my answer nicely. So I'm going to 6a, I'm going to continue it down here, or conclude it, I'll call this. So the end of this is to change the y to the appropriate f inverse of x symbol. And when I do this, I'm going to write the y on the left-hand side as opposed to the right-hand side. So my answer to 6a, the inverse of my function, f inverse of x, is going to equal the cube root of x plus 5. Part B is the tricky one, and it gives me the option of doing one or the other. I'll do the left one just because it's written first, and it's not even, they're equally hard. So to do part B, it says to do one or the other. I'll do the left one. You'll get the same result if you do the right one. To show algebraically that your inverse answer to part A is correct, you have to do this composition. It's kind of like a mini proof, and it has to simplify to be x. So I need to find f composed with f inverse of x. And of course, I know that that means f of f inverse of x. And what does that tell me to do? That tells me to go to the f function, which is x cubed minus 5, and I'm going to change that to f inverse cubed minus 5. So I'm going to get f composed with f inverse of x equals to f inverse of x cubed minus 5. All I did is change that x to that f inverse, and now I'm going to change the f inverse to the cube root of x plus 5 because that's what it's equal to. So I'm going to get f composed with f inverse of x equals to, and I'm going to change that symbol to the cube root of x plus 5. So I get the cube root of x plus 5 cubed minus 5. And the nice thing about the parentheses here is the cube root and the cube cancel each other out. And that's going to leave me with f composed with f inverse of x equals to, this whole thing just comes out to x plus 5. You don't need the parentheses anymore. You don't need the cube root or the cube. They all cancel away. And I still have this minus 5. And the beautiful thing is, this left-hand side I can continue to write as f composed with f inverse of x. And the right-hand side, the 5's cancel, and I'm left with an x. And that's exactly what this asks me to do. Show that f composed with f inverse of x equal to x. And I just did the 4 steps to do that. Because when I found f composed with f inverse, because it's simplified exactly to be x, then I know that these two functions are inverses of each other. Only functions that are inverses of each other, when you compose them, do you get x. All right. Problem 7 has a heap of parts, and it asks me to describe the transformations compared to 2 to the x. And let me find the function first and then describe the transformation, because the instructions say find the requested function, describe the transformation compared to 2 of x. So to do g of x plus 5, because the x plus 5 is in the parentheses, I'm going to change the x in the exponent to an x plus 5. And an exponent kind of works like a parenthesis, so I don't really need to put the x plus 5 in a parentheses. That's the find each function. And then hopefully by now you know the left, right, up, and down shifting. This is going to shift the graph to the left because the thing is in the plus is in the parentheses. So to describe the transformation, I'm just going to say it shifts left 5 units. I'll do g of x minus 4 essentially the same way, meaning I'm going to change the x in the exponent to an x minus 4. I really don't need a parentheses when I go to find each function because the exponent works as a parentheses. But if you put a parentheses and did 2 to the parentheses x minus 4 power, it looks weird, but it's not wrong. It's rare to see parentheses and exponents unless it's a really complicated exponent. So the find each function, either one of those would be okay. And a minus inside a parentheses is going to shift the graph to the right. So to describe the transformation, I'm just going to say it shifts it right. Four. The next two, the parts C and D, because the number is not inside the parentheses, when you go to find each function, this plus 1 is just going to go after the function. So it's just going to be the g of x function plus 1 for the find each function. And then when the the addition or subtraction is not inside the parentheses, and it's after the function notation. A plus is up, which is going to be for this part. The minus is down, which is going to be for the next part. So to describe the transformation, I'm going to say it shifts it up 1. This as a function, that minus 3 is not in a parenthesis, so it's just going to go after the 2 of x, the 2 to the x, which is a g of x function, and it's going to shift the graph down. And in this case, it's going to shift it down 3. I'm not having to do any graphs. I'm just finding the function and describing the transformation. E, the negative is just going to go right in front of the function, so this is for finding each function. It's just going to be negative 2 to the x power, and negatives in front of the function reflects the graph over the x-axis. In part F, because the negative's in the parentheses, the negative's going to go with the x in the exponent. To find each function, it's going to be 2 to the negative x power. And when the negative's in the parentheses, the graph gets reflected over the y-axis. When I do the find each function for part G, this x plus 3, because it's in the parentheses, has to be in the exponent. The plus 5, because it's after the function, goes after the function. The plus 3 inside the parentheses moves the graph left 3. The plus 5 after it moves it up 5. So we're going to say it shifts it left 3 and up 5. For part H, the x minus 3 in the parentheses goes in the parentheses in place of the x. The minus 2 that's not in the parentheses goes after the function. That's the find each function. And then for the shifting, the minus 3 inside the parentheses is going to shift it to the right 3, and the minus 2 afterwards is going to shift it down 2. There's a microscopic negative written there. When I go to write this, that negative needs to be for the find each function to the left of the 2, and the x plus 1 needs to go in a parenthesis in the exponent because it's in a parenthesis. The negative, when I go to describe this, the negative in front of this is going to reflect it over the x-axis. And the plus in the parentheses shifts it to the left 1. So hopefully we've done so many of these this semester that this is just kind of second nature to you now. To find each function here, this negative's going to go in front of the 2. That negative's going to go in the exponent. That negative reflects it over the x-axis. That negative reflects it over the y-axis. So for the explanation of the transformation, we're going to say it reflects over the x and the y-axis. So we're done with 8 of 30 problems, so it's going to be a ways to go. 8 through 11, we need to write each side with the same base, and this means that probably one of the numbers, one of the bases is a power of the other base. And in problem 8, that 27 is 3 to the third power. So to get started on problem 8, I had to know my powers of 3 up to 27. And now I can rewrite this problem as 3 to the x minus 3 equals 3 cubed. And once you can write both sides with the same base, you can drop the bases and set the exponents equal to each other. So what I've done here is I've canceled out that base, and I set the x minus 3 exponent equal to the 3. And now I'm going to solve for x by adding 3 to both sides. This is going to give me x equal to 6 for my answer. It says be sure to check, so let me check this real quickly. For checking, I should go 3 to the 6 minus 3, and that should equal 27. I should change that x to 6. If I simplify that exponent, that's going to give me 3 cubed equal to 27, and it works just fine. Nine is real similar. For 9, the 16, I'm going to need to rewrite it, and I need to know my powers of 2, but not so many of them. To do number 9, I'm going to rewrite the 16 as 2 to the 4th power. And once you get both sides written with the same base, you can drop the bases and set the exponents equal to each other. And now I'm just going to solve for x. And my answer is going to be x equal to 3. And it's going to check real easily. I'm not going to check it just to make sure I don't run this too long. The next problem I'll check is a little bit messy. For problem 10, I have to rewrite each of the fractions with a negative exponent using the 1 over x equals x to the negative 1 kind of rule. So I'm going to rewrite 1/2 as 2 to the negative 1. And I'm going to write 1/8 as 8 to the negative 1. I can't forget the exponent on the left-hand side. And ultimately, I'm going to need to change that 8 to have an exponent. And so we remember how we put that parentheses on the right-hand side to facilitate that change. So now I have it set up so I can get the bases kind of the same. And the 8 is a power of 2 because 2 to the 1st is 2, 2 squared is 4, and 2 cubed is 8. So now I can rewrite the right side so it has the same base as the left side. So now I'm going to have both sides written with the same base, but both sides have 2 parentheses, and I need to clear those parentheses by multiplying the exponents. On the left side, I'm going to multiply negative 1 times x and negative 1 times negative 2. And when I clear the parentheses, I'm going to get 2 to the negative 1x plus 2, because negative 1 times x is negative 1x. Negative 1 times negative 2 is positive 2. And on the right-hand side, when I clear the parentheses that I created, I'm going to multiply 3 times negative 1 and get negative 3. Now I have both sides written with the same base, so I can drop the bases and set the exponents equal to each other. So I'm going to go negative 1x plus 2 equals negative 3. Now I'm going to minus 2 from both sides. That's going to give me negative 1x equals negative 5. And then I'm going to divide both sides by a negative 1. And for my answer, I'm going to write x equal to 5. I'm going to attempt to check it right over here. So for checking, especially because the problem was pretty complex, it's a good use of my time. The original problem is 1/2 to the x minus 2 equals to 1/8. So it should be the case that 1/2 to the 5 minus 2 equals 1/8. I'm going to check this on my calculator, but I really don't have to. And before I break out my calculator, I'm going to get that exponent simplified. And on my calculator, to do that, I'm going to go parentheses 1 divided by 2, parentheses up arrow 3, and then have to math enter to get it into a fraction because it's going to give me a decimal. So on clear parentheses 1 divided by 2 up arrow 3, decimal, math enter, and that's perfect. It gives me 1/8 equals to 1/8, and that's exactly what I needed for my checking. So I know my answer is perfect. I don't need to go further with the checking. problem 11, I need to write each side with the same base, and on the left-hand side, I'm multiplying two terms with the same base. To get the left-hand side written with a single base, I'm going to add the exponents using the rule that says if you're multiplying terms that have the same base, that you can combine to a single term if you add the exponent. So that's kind of what I use. It's exactly what I use to simplify the left-hand side to have 1, 2 as opposed to 2. Now in the exponents, the numbers have opposite signs. I'm going to combine those by subtracting and taking the sign of the larger. Now I have each side written with the same base. I can drop the bases and set the exponents equal to each other. And I'm going to solve for x by adding 1 to both sides. That will give me 2x equal to 6, and then I'll divide by 2. I'll get an answer that I'm going to check because it won't take that long, and it's kind of a complicated problem of x equal to 3. For my checking, probably going to use my calculator, and I should go to the original problem, which was 2 to the 2x minus 4 times 2 cubed equals 2 to the 5th, and plug in 3 for x. So I get 2 to the 2 times 3 minus 4 times 2 cubed equals 2 to the 5th. This exponent becomes 6 minus 4, which is 2. So this is going to be 2 squared, 2 squared times 2 cubed equals 2 to the 5th. I can do this by hand or on my calculator. 2 squared is 4, 2 cubed is 8, and 2 to the 5th is 32. So this whole thing, even without my calculator, both sides come out to be the same number, so I know my answer is correct. 12 is the only really fully by hand graph that we're doing. Graphing a logarithmic function, and that's a bit of a mess. So when we graph logarithmic functions, if we're not giving a graph just to shift around, generally we take the function and we write it in exponential form. So to get started with 12a, the initial function, if I write it with the log on the left-hand side, it might be easier, says the log base 2 of x equal to y, and I'm going to write a version of this without a logarithm. I'm going to cross out the logarithm. The 2 is going to remain the base. The equal sign is going to remain where it is. The y is going to move to the left-hand side. The x is going to move to the right-hand side. When the x moves to the right-hand side, it doesn't need to be in a parentheses. And when the y moves to the left-hand side, I'm creating a function that has an exponent. The y needs to be that exponent. So this is the function I'm going to use for my table rather than the logarithmic function. And every time I graph logarithms by hand, if I'm not shifting a graph, I use the same 5-valued table. The bad thing about the table is that the numbers go in the x column, or in the y column, and not the x column. Now for each number in the y column, I need to get a corresponding x. It's real easy to do because all I'm going to do is plug this number in. So the first one, I'm going to go x equals 2 squared by taking this 2 and plugging it in for that y. 2 squared I don't need my calculator for. That's a 4. That's going to be the first point on my graph. Might as well go ahead and graph that point right now. Next thing I'm going to do is plug in 1 for this. I'm going to go x equals 2 to the first. Anything to the first power is itself. So I'm going to get a 2 there. And now I'm going to plot that second point, which is 2, 1. And then I'm going to plug in 0 for that y. I get x equals 2 to the 0. Anything to the 0 power is 1. That's going to be the point 1, 0. Then I'm going to get x equal 2 to the negative 1. For me, it's easier to graph decimals than it is fraction. I'll go 2 up arrow negative 1. I get 0.5. I could write 1/2. It's up to you. If you want to write 1/2, it's fine. If you want to write 0.5, it's fine. I'm going to write 0.5 because I graphed that better. And then 0.5 negative 1 is about right there. And the last point I'm going to do, I'm going to plug negative 2 in for that y and get x equals 2 to the negative 2. And again, I can go 2 up arrow negative 2. I get 0.25 or 1/4, whatever you prefer. I do better at graphing decimals sometimes than fractions, so I'm going to write 0.25. You can write 1/4 if you prefer that. And 0.25 negative 2 is about there. So I've made my table of values. I've plotted the points. Before I sketch the graph, I'm going to put that vertical asymptote in. All logarithm graphs have a vertical asymptote right at the edge of the domain. So if I do part B to find the domain of the function, that will help me get my vertical asymptote and help me get a better looking graph. So to find the domain of a logarithmic function is really easy. You just take the argument and set it greater than 0. There's no algebra really to do for part B. The domain of any logarithm, you take the argument, in this case x, and set it greater than 0. So that's the domain, and that tells me right through x equal to 0, if I put a vertical line there, or dash vertical line, that on the graph is going to serve as a vertical asymptote. This is a graph, a line that the graph won't touch nor cross. And the graph won't exist on two sides of it. The graph only exists where x is bigger than 0, which is to the right of this. So when I go to do my graph, there's going to be no graph to the left of that line because that's not part of the domain. Now I'm going to connect the points, keeping the vertical asymptote kind of in mind that I just kind of drew in. And I'm going to keep my graph microscopically close, but just to the right of that line, and then follow the points up and to the right. So that seems like a reasonable graph for number 12. That's the only graph that you have to fully do by hand. The rest of the graphs we're going to do by shifting. So problem 13 gives me the function. It wants me to find f of x plus 1, and it says f of x equals the log base 2 of x. So f of x plus 1 is simply just going to be the log base 2 of x plus 1. That's the answer to part A. To find the requested function, I just need to change the x to x plus 1. How do I state the domain? Simple, we just did the domain. To do part B of number 13, to find the domain of any logarithmic function, we just take the argument and set it greater than 0. So I'm going to go x plus 1 is greater than 0. I'm going to minus 1 from both sides and get the domain written as an inequality as x is greater than negative 1. To describe the transformation, I already know that f of x plus 1, because it's a plus inside the parentheses, we're going to shift the graph left 1 unit. Now I want a graph, and I'm going to use the graph that I was given to do my graph. I'm going to draw a vertical asymptote at negative 1 on the x-axis because the domain starts at negative 1, which means I get a vertical asymptote that goes through negative 1. And now I'm just going to take each point and shift it. And I'm going to shift each point to the left 1 and make a new point. So this point right here is going to shift left 1. This point is going to shift left 1. This is going to shift left 1. This is going to shift left. And that's going to shift left. And as I go to create my graph, I was going to go right to the right of that vertical asymptote and just follow the points that I connect. Missed some of the work there. Question 14, we start off with the function f of x equals the log base 2 of x, and I'm asked to find f of x minus 1. Because the minus isn't in a parentheses, this is just going to be the log base 2 of x minus 1 To find the domain of any logarithmic function, we just take the argument and set it greater than 0. This minus 1 is going to have nothing to do with the domain. The argument is just this x in the parentheses, and I'll set it greater than 0, which means when I go to graph this, I'm going to have a vertical asymptote that goes through 0 on the x-axis, which is actually the equation of the y-axis. The transformation, because the minus is afterwards, it's going to shift the graph down 1. And to do that, I'm going to just make my graph by taking every point and moving it down 1. These points that are away from the asymptote are easier for me. So this point I'm going to move down 1. That point I'm going to move down 1, down 1, down 1, down 1. This vertical asymptote is still the same, and the graph is just all shifted down 1. So that's a reasonable, maybe not stellar graph, but good enough for us. We start off with the function f of x equals the log base 2 of x, and we're asked to find f of x minus 3 plus 2. So the x minus 3 needs to go in a parentheses, and the plus 2 goes afterwards. For the domain, because any logarithm, you find the domain by setting the argument greater than 0. I'm just going to set the x minus 3 that's in the parentheses greater than 0. I'm going to add 3 to both sides and get x is greater than 3 for my domain. Which means through 3 on the x-axis, when I go to do my graph, you're going to have a vertical asymptote there. To describe the transformation, the minus 3 in the parentheses is going to shift the graph right 3. The plus 2 moves it up 2. Which means for every single point, I need to move it right 3 and up 2. So this first point here, I go 1, 2, 3 to the right, and then 1, 2 up. This point, I go 1, 2, 3 to the right, 1, 2 up. This point, 1, 2, 3 to the right, 1, 2 up. Well, landed right on that point. This point, 1, 2, 3 to the right, 1, 2 up, and then 1, 2, 3 to the right, 1, 2 up. So I'm going to butt up to this new vertical asymptote, and every point got moved exactly right 3 and up 2. So for rigid transformations, which means reflections, moving the graph left or right or up or down, you can simply take the points and move them without having to create a new table of values. I have a table of values handy for the non-rigid transformations, and I'm going to need that in question 16. So in question 16, the original function is f of x equals the log base 2 of x. I'm asked to find negative 2 times f of x. That's just going to be negative 2 times the log base 2 of x. I'm just going to take negative 2 and multiply it by the log base 2 of x. The domain, I just set the argument greater than 0 and get x is greater than 0, which means I'm going to have a vertical asymptote at 0, which is the y-axis. To describe the transformation, this is a sneaky one. The negative in front of the 2 is going to reflect it over the x-axis. So part of the transformation is it reflects over the x-axis. That's the easy part. The number in front of the function, if it's bigger than 1 absolute value-wise, it's going to stretch the graph. If it's less, in between 0 and 1, it shrinks or compresses the graph. This is going to stretch the graph out. And so we're going to say on top of reflecting over the x-axis, it's going to stretch the graph. Now I have to do better, because this is a non-rigid. Once you stretch, you can't just move the points. You have to play with the table. And it's going to be really easy to do the table here. I'm going to use my given table to get the table of points that I'm going to graph. The original table in the x column had 0.25, 0.5, 1, 2, and 4. And all I'm supposed to do is take each y and multiply it by -2. So to get my graph, I'm going to take each one of these y's and multiply it by -2, because -2f of x just implies to multiply all the y's by -2. So first y, -2 times -2 is positive 4. Second y, -1 times -2 is positive 2. Third y, 0 times 2 is -2 is 0. Fourth, 1 times -2 is -2. Fifth, 2 times -2 is -4. If I plot those points, it's going to do everything. Because I multiplied by a negative, it's going to do the reflection over the x-axis. Because I multiplied by a 2, it's going to stretch it. So 0.25 and then 1, 2, 3, 4 is about there. 0.5 and then 1, 2 is about there. 1, 0 I already have marked. 2, -2 is about here. And then 3, 4, 1, 2, 3, 4, -4 is about here. So you can see that it gets flipped over. It got reflected over the x-axis. So instead of going down towards the vertical asymptote, it goes up towards the vertical asymptote. And it got stretched a bit too. It got steeper as it was flatter, the original one. The new one gets stretched a little bit. It gets pulled further away from the x-axis. All right, so that's a pretty decent graph. So let me move on from these. And 17 through 19 are easy to write the expression as a single logarithm. First, I make any exponents into coefficients, and then I use the rules to make multiple logarithms into logs. So first, for problem 17, I'm given 2 logarithms. I'm asked to rewrite something that's equal to this that only has 1 logarithm. The first step is to take the exponents, or make exponents out of the coefficients. And then I'm going to write 1 logarithm with the appropriate base. If there's no minuses, there's no fractions. If there is a minus, I get a fraction. In this case, there is a minus, so I get a fraction. And any letter who has a minus in front of its logarithm goes in the denominator of the fraction. Any letter that doesn't have a minus in front of it goes in the numerator of the fraction. So real quickly, what I did here is I made coefficients, which are numbers in front of the logarithms, into exponents. That was my first step. And then I wrote 1 log with the correct base. If there's no minus, there's no fraction. If there is a minus, we get a fraction, and any letter with a minus in front belongs in the denominator. So if I was doing the same kind of thing for number 18, I'm going to write the ln of x to the 5th minus the ln of y squared plus the ln of z. So I made the coefficients into exponents. Now I'm going to write 1 logarithm with the appropriate base. In this case is e. I scan. If I didn't see a minus, I wouldn't have a fraction. Because I see a minus, I get a fraction. The only letter that's going to go in the denominator is a letter that has a logarithm with a minus in front of it. So the y squared is the only letter that's going to make its way to the denominator. Neither the x to the fifth nor the z belong in the denominator because their logarithms don't have minuses in front of them, so they have to go in the numerator. So that would be my answer to 18. In case I didn't explain it, that was my answer to 17. For problem 19, same thing. To write from 3 logs or 2 logs down to 1 log, first, for each logarithm, any numbers that are in front of the logarithm, you drag inside the logarithm and make an exponent. So I made the x squared and y to the fourth. And now I'm going to write 1 logarithm with the appropriate base. In this case, it's a 3. If there wasn't a minus, I wouldn't get a fraction, but there is a minus, so I get a fraction. Any logarithm who has a minus in front of it will have its letter go in the denominator. So the y to the fourth and the z will both belong in the denominator because their logarithms have minuses in front of it. And the x squared doesn't have a minus in front of its logarithm, so it goes in the numerator. For 20 through 22, and then we'll probably break for a part 2. To expand, I need to write 1 logarithm for each letter. So here we're asked to expand from 1 log to multiple logs. So I'm going to write 1 logarithm for each letter. And the signs that go between are either plus or minus. Minus if the letter's in the denominator. So to get started on number 20, I'm going to write 1 log for each letter. Very specifically, 1 log for the y, 1 log for the x squared, and 1 log for the z. So that's the beginning of this. I'm writing 1 log for each letter with the appropriate base. The signs that go between are pluses and minuses. Minus if the letter's in the denominator. The x is in the denominator, so I get a minus in front of its logarithm. The z's in the denominator, so I get a minus in front of its logarithm. If it's not in the denominator, you get a plus in front of it. Lastly, we're going to make exponents into coefficients. So my answer for problem 20, I have the 3 logarithms. The second logarithm, I'm going to bring a 2 out in front of it because of the exponent. For problem 21, the problem has 3 letters. I'm going to expand it to 3 logarithms. So I'm going to get a natural log of x squared, a natural log of y, and a natural log of z. So I wrote 1 logarithm for each letter. The only signs that go between are plus and minus. You get a minus if the letter's in the denominator, so the z logarithm gets a minus in front of it. The y logarithm, because it's from the numerator, gets a plus in front of it. Done with that step, now I'm going to make exponents into coefficients and get my answer. So my answer for problem 21 is going to be 2 times the natural log of x plus the natural log of y minus the natural log of z. If it bugs you that I don't have the arguments in parentheses, you can throw them in parentheses. If I'm not using my calculator, it's hardly that big of a deal. I generally don't put the parentheses in. Same deal for 22. I'm going to write 1 logarithm for each letter. The base is going to be 4. So I'm going to get the log base 4 of x cubed, the log base 4 of y squared, and the log base 4 of z to the 5th. None of the letters are in the denominators. The only signs that can go between are pluses and minuses. You only get a minus if the letter's in the denominator. So the signs that go between are a couple of pluses. And now I'm going to make the exponents up front of the logarithms and get my answer. So I'm going to get 3 times the log base 4 of x plus 2 times the log base 4 of y plus 5 times the log base 4 of z. The second half of the video is going to be shorter, but it has the word problem. So we'll just stop right there and we'll do a part 2 here in a little bit.